Good evening, sir.
Yeah, good evening. Okay, we'll start slowly. I think 8 students are there. So, syllabus for the term test is chapters 1 to 8, except chapter 5. Chapter 5 is not there. You can see the screen.
Yes, sir.
Yeah, so we'll start slowly. Any questions, doubts, concerns?
Sir, இன்னும் படிக்கவே ஆரம்பிக்கல சார்.
But we have been preparing for tests, no?
Yes, sir. ஆனா இந்த டெஸ்ட்க்கு இன்னும் படிக்க ஆரம்பிக்கல.
I mean, the syllabus is same.
Okay, sir.
Test is so one day is there, no? We'll just focus on the concepts I discuss. So tomorrow you have school, no?
Yes, sir. Yes, sir.
Full day. So and regular timing, no? 3:30 will close. Okay, the first thing I want to discuss is dipole. In uniform external electric field. Okay, and dipole is nothing but two small, two opposite charges, minus q and plus q, separated by a small distance. QA. Okay, and there's the electric field V towards right. So the force that is acting on them, the net force will be 0 because on one of them. On the positive charge, the force will be towards right. Force on a charge in the electric field is the value of the charge into the electric field, and the force on this negative charge will be towards left. Okay, so the net force in uniform electric field is 0. Force is a vector, but it's not non-uniform force means here the electric field could be different. On the plus one will be E1, and in the second minus Q will be E2. So then the net force will be QE1 minus QE2. If it is non-uniform electric field, that means electric field is changing from point to point in space. So in that case, the net force is not equal to 0. But U1 equal to E2 means the net force will be 0. That's the case of uniform electric field. But in uniform electric field, since the two forces are acting at different locations, there will be a torque. So this force will produce a clockwise torque. This thing, both minus q and plus q are of same mass. So if it's going to rotate, it will rotate about the center. So about this center, this force plus QE will produce a clockwise torque, and this force minus QE will also produce the same clockwise torque. So torques will add. So the net torque on this dipole is not equal to 0. Okay. So it will rotate, but no translation motion. It will just rotate, and it will rotate until it becomes horizontal position. Once it becomes horizontal, once the dipole becomes like this, plus Q and minus Q. So at this position, the force on the plus Q will be towards right, and force on this minus Q is towards left. And this thing will not produce any torque because torque is force into the perpendicular distance. Okay, so here this is the axis about which it's going to rotate. Okay, so the perpendicular distance of this force from this axis is 0. So when this force was in this previous one, the force was here, right? So this is the axis about which it's going to rotate. So the distance of this force from this axis is this distance. This distance is the perpendicular distance of the force from the axis. So because of this distance, there will be a torque. But once the force is like this, the torque is 0 because our perpendicular distance is 0. At this particular location, our perpendicular is 0. Okay, so this is like a stick. At two ends of the stick, you pull the sticks outwards by equal force. The stick will get maybe stretched a little bit, but it will not rotate. Okay, so but from this, so at this position, the net force and net torque both are 0. Okay, so this is the equilibrium position. Equilibrium position means net force and net torque should be 0. Net force is always 0 because it's plus Q E and minus QE, but the torque will be 0 at this particular position. So from this position, if I displace this dipole a little bit on, say, this side, displace a little bit on this side, okay, then I should figure out whether this thing will come back to the original position. So when I try to displace this a little bit towards this position, okay, so plus Q will be here, minus Q will be here. So here the torque, the force will be QE this way, and this minus Q will be towards left. Okay, so this force will try to produce a torque this way. Okay, and this force will produce a torque this way. So it will come back to the original position. So this is a stable equilibrium position. Equilibrium means the net force and net torque should be zero. Net torque is zero because the perpendicular distance is zero. And stable means I have to disturb it from this equilibrium position a little bit and see whether it will come back to its original position. Okay, here it is coming back. So this is the relation of P. Direction of P is from minus Q to plus Q. Okay, and electric field is also towards right. So when P is parallel to E, it's equilibrium and it's a stable equilibrium. So the other situation is anti-parallel. So now if I consider minus Q on the right side, now if I consider, okay, here it's plus Q and here it is minus Q. Okay, so this position also is stable equilibrium position because the net force is zero, which is always true in uniform electric field. And here the torque, the force on this one is towards left, QE, and the force on this one is towards right. I should draw it properly, right? So right now this thing is going to compress this sort of the dipole. So, but there is no torque. Torque is again zero because our perpendicular distance is zero. Can I assume this is a stick? I'm compressing the stick from both the ends. The previous one is, this is a stick. I'm stretching the stick from both the ends. So it will not rotate. I'm stretching the stick from both the ends, this way and this way. So it will not rotate, but it will get stretched a little bit. But here I'm compressing the stick from both the ends. Okay, so this also not rotate. And we'll get, so torque is zero and external force is also zero. So this also equivalent position. Now we have to figure out whether it's stable or unstable. So for that, I have to disturb it a little bit from the equivalent position. So let me rotate this minus Q. See a little bit on this side. So this is a new position of minus Q and the new position of plus Q. Plus Q minus should be diametrically opposite. Okay, so now the force on this one is this way towards left. On this one will be towards right. So if you think carefully, you can see that this force will produce a torque. This force will produce a torque in this direction, clockwise direction. And this force will produce a torque in this clockwise direction. So we'll take it away from the equilibrium position. So this is an unstable equilibrium. This unstable equilibrium. So here the P is from minus 2 to minus P to plus Q. So P is towards left and electric field is towards right. So when P is anti-parallel, when P and E are anti-parallel, or we can say the angle between them is 180 degrees. It's an unstable equilibrium position. When P and E are parallel, it's a stable equilibrium position. Here P is towards right, minus Q to plus Q, and E is also towards right. So the angle between P and E is 0 degrees. So it's a stable equilibrium position. But when angle is 180 degrees, here P is from minus Q to plus Q, it's towards left, but electric field is towards right. So this is an unstable equilibrium position. So this also consistent with the formula for the potential of this dipole in external electric field. Potential of the dipole U is minus P dot E. Okay, so stable equilibrium position will correspond to U being minimum. Okay, and unstable will have U as maximum. So since negative sign is already there, so whenever this is maximum, okay, or positive maximum, this thing will be stable. So this I can write as P E cos theta. P is fixed because dipole is fixed, electric field is external, electric field is fixed. The only variable is the theta. Okay, so cos theta will vary from -1 to +1. Like sin theta also will vary from -1 to +1. So U minimum value will be -1 when cos theta is +1. U minimum is -1 or I should say u minimum is minus 1 into PE, so it's minus PE. Okay, and u maximum is plus PE. That will happen when cos theta is minus 1. So u maximum is plus PE. Okay, so u minimum minus PE corresponds to cos theta being 1. That means theta is 0 degrees because cos 0 is plus 1. Okay, and this thing will correspond to cos theta being cos being minus 1. That corresponds to theta equal to 180 degrees. Okay, so this x-axis, y-axis. So 0 degrees correspond to this point. Here cos is plus 1. So 180 degrees, this is the point. So cos is minus 1 here. Because cos is defined as x by r. So at this particular point, x is r. At this particular point, x is minus r. Where r is this distance. Okay, so this is basic of cos. So what I want to say is, one thing is we figure out whether it's stable or unstable by disturbing it and finding the direction of the torque. Another way is we can use this formula of potential energy, and you have to use this basic concept that stable equilibrium position correspond to potential energy being minimum. Okay, so unstable equilibrium position correspond to potential being maximum. The analogy in the gravitational cases, so this is the hill and this is a valley. Okay, so here the gravitational potential which is mgh will be minimum here, and here the gravitational potential is mg. Let me call it h2, and let this height be h1. So this position is where the mass is here. This is stable equilibrium position, because if we disturb this mass a little bit towards right or towards left, it will come back to this equilibrium position. But suppose the mass is here and it distribute a little bit on right or left, it will go down. It will go away from the equilibrium position. So this is stable equilibrium position, which corresponds to minimum energy. And this is unstable, which corresponds to maximum potential energy. Is it clear?
Clear, sir.
Yeah. So stable equilibrium position of a dipole corresponds to P and E being parallel. That you can straight away get from if you remember this formula. Because potential should be minimum. For that P dot E should be maximum. It should be like plus PE. So for it to be positive, theta should be 0 degrees. So P and E should be parallel. Okay. Next concept. Suppose I have a charge here. Say this is first, I'll take a square of some length, and let the charge be at the center. Let it be Q1. Okay. Now I want to take a second charge Q2. Okay, and I want to move it from here to here. This is the final position. This is the initial position of Q2. Q1 is fixed. So what is the work done to move this charge? First of all, will the work be required to move the charge? You can figure that out. Let me assume Q1 and Q2 are like charges. Q1, Q2 are like charges. Okay, so there will be force of repulsion, right? So on this Q2, there will be a force of repulsion in this direction. Okay, so that I can say split into two components. One is towards this one, and one is towards this one. So this Q2 will experience a force vertically downwards and towards the right. So I have to overcome this downward force and move it upwards. So I have to do some work to move from here to here. Until up this point, that will be true. Okay, but once I reach this point, the repulsive force will be in this direction. So the horizontal component will be towards right and the vertical component will be towards upwards. So I don't have to do any work to move it up, but I have to apply some force to negate this horizontal force. So basically, there will be some work required to move this charge from here to here. So how do I find that work done? Any idea? Work done to move in a small displacement. dW is F dot ds, where F is the force I have to apply to make it move through a small displacement ds. Okay, this is class 11, this one. Another thing is a potential at a point is work done to move the charge. Actually, you can say 1 coulomb charge from infinity to the point P. Okay, another concept is that work done to move a charge between 2 points of potential difference. V is Q into the potential difference between those 2 points, say V2 minus, or I can say V final minus V initial. Okay, so this you can take it as a basic formula. This comes from the definition of the potential, that potential at the point is work done to move 1 coulomb charge from infinity to that particular point. So potential at this point, I can see the work. Okay, so if I use this one, what is potential at this initial point? This is the initial point, right? This is my initial point, and this is the final point. So what is potential initial point due to this Q1? Anyone? Potential at the point due to point charge. What is the formula for potential due to point charge? Potential due to point charge
Q
is
by R, sir.
K into, so Q1 by
Q1 by R1.
Yes, whatever is this distance. Okay, let me call it R. So at this initial point, the potential will be this distance. Let me call it R1 only. Okay, let it be R1. This is the initial potential. Similarly, for the potential at this final point, EF is K Q1 by R2. Okay, so and potential is scalar. There is no this one. So Q1 is same Q1 here, and R1 will be equal to R2. By symmetry, right? It's a half diagonal of a square. Okay, so R1 equal to R2. So V1, Vi, and Vf are same. They are the same potential. So the work done will be 0. Okay, and so that's what I initially argued physically. So to moving from here to here, I have to do some work because the external force is downwards. The repulsive force component is downwards. So I have to do some work. But when going from the middle point to the upward point, the repulsive force will actually push it. So the work done here is negative. Here, the amount of work done to go from the bottommost point to the middle point is positive, because work is actually required to overcome the repulsive force. So from here to here, positive work is done. Okay, and from here to here, negative work is done. So the work done from here to here, the total work done is 0. So as far as this question is concerned, the basic thing you have to remember is the work done to move a charge from one point to another point is Q the potential difference between the 2 points. This comes to the basic definition that potential point is work done to move 1 coulomb of charge from infinity to that point. So the work done to move Q coulombs of charge from infinity to that point will be Q times this one. So that should give an idea why is this Q to EF minus VN. So is this concept clear?
Sir.
Yeah. So I hope you remember these things because we were discussed while studying chapter 2. So if you have 2 cells or cells in, okay, let me take 2 cells only. So this is first cell, second cell. It has got an EMF E1, and the second cell has got an EMF E2, and the first cell has got internal resistance R1. So there's small resistance here because it's not ideal, it's a real cell. And this has got a small resistance R2, internal resistance R2. So this can be represented as a single cell of some equivalent EMF and a equivalent internal resistance. So what is the relation between equivalent and what is equivalent in terms of E1 and E2? So if I remember correctly, E equivalent is sum of E1 plus E2. So E equivalent will be E1 plus E2 and R equivalent will be R1 plus R2. Okay, so I can have n of them up to Rn. So the EMF will become so on up to En. And this resistance will also add up to Rn. So for series, it is easy. But if it is in parallel, E1 and E2, and I want to replace with a single cell. So here, it's not very okay. E equivalent is the corresponding the R equivalent. So R equivalent is, if you remember, it will be 1 by
1 by R1 plus 1 by R2.
It's 1 by R1 plus 1 by R2, and then E equivalent by R equivalent is E1 by R1 plus E2 by R2.
E2 by R2.
E1 by R1 plus E2 by R2. So there are n of them. I just have to add so on up to Rn. And this will become so on up to En by Rn. Okay. So if we take these two cells, the terminal voltage here, just take the series combination. So this is the terminal voltage, which is called V. Okay, that will be equal to E equivalent. So this cell will drive a current in this direction. I. Okay. So V is dropped from, and this will be a positive terminal, this will be negative terminal, and V is dropped from this positive terminal, negative terminal. That will be this E equivalent minus I into R equivalent. Is that right? It is correct, but R equivalent is here. Is R equivalent. Okay. Because V is dropped from. Just a minute. Now it's a problem. E is dropped from this to this. So from here to here, there is a drop of E. Okay, and the current is flowing towards left. So along a resistor, if I move against the direction of current, there will be a voltage rise. So I put a minus sign there because V is dropped from left to right, from plus to minus. So there is a drop of V equivalent across the cell, but here there is a voltage rise because we are going against the direction of current. So it will become minus. So this is the basic relation. So if I plot V versus I curve of this particular equation, V versus I. So this is will look something like this, right? Because the slope is negative. Okay, so from this I can. So this I equal to 0. So this value of voltage, okay, that corresponds to I equal to 0. So that will be equal to E equivalent, right? Okay, and E equivalent series is E1 plus E2. So suppose they say there are 5 cells in series, and this intercept is say 20 volts. Okay, so what is EMF of, and they are identical cells. So E1 equal to E2 equal to E5. Okay, they are identical cells, and the graph is looking like this. So the y-intercept will correspond to this E equivalent, because this is the relation, right, between voltage and the current, between the terminal voltage V and the current coming out of the cell. So according to this equation or this equation, so the I equal to 0 corresponds to y-intercept V being equal to V E equivalent. So this value 20 is E equivalent, which is equal to E1 plus E2 plus 1 to E5. That is equal to 5 E1, which is equal to 20. So from that I get the EMF of a single cell as 20 by 5, that is 4 volts. So they will say there are some N cells in series, and the VA characteristics of the cell or the battery, which is the terminal, it's like this. So given this graph, I have to find the EMF of single cell. Okay, so looking at this curve, I can say the y-intercept is E equivalent. Y-intercept we get by putting I equal to 0. That will be E equivalent, and E equivalent is E1 plus E2 plus E3, so on to E5. These are 5 cells, and all cells are the same. So it's 5 times E1. From the ideal EMF of a single cell is 4 volts. Is this concept clear? Yes.
Yes, sir.
So mutual interest between two coils. They have two coils here, coil 1 and then coil 2. Okay, 1 and 2. So mutual inductances, one of them may pass the current, and what is the flux linking the other one? So in any coil, I can pass a current, say I1. Okay, because of that, there will be some flux linking the second one. Let me call that flux phi2. So I can say I1 is input and phi2 is output. So phi2 is equal to the input I1 as the mutual inductance between these two, M21, and this flux is total flux linking the second one. So N2 phi2 is M21 into I1. So this is the basic relation for mutual inductance. The input is the current in one of them. Okay, and the output is the flux linking the other one. So the output is proportional to the input, and the proportionality constant is the mutual inductance M21. Okay, so if I decrease the distance between these two coils, what will happen to M21? See, basically, whatever flux, this is a solenoid, no? So the magnetic flux can come out like this. This is a north pole of a magnet. Actually, it can go. Okay, so it'll go like this. And it'll come back like this. Okay. So some flux will pass through this one. All right. So the flux phi2 will be more. Suppose I want to increase the flux phi2 linking the second coil. So what can I do? Should I increase or decrease the distance between them? I can decrease the distance between them. So one way to increase the flux linking the second coil is to increase phi2, which is linking the second coil. I can decrease the distance between the two. Okay. Another way to increase the flux linking the second coil is I can increase the number of turns of the second coil. Because this is the flux linking the second coil, the total flux linking the second coil. So one way is to decrease the distance between 1 and 2, because the source of this flux is the current I1. Okay, so this magnetic field lines, if I bring this thing closer to this one, more number of field lines will pass through this second coil. So that way I can increase the flux linking the second coil by decreasing the distance between the two of them. Another thing is I can decrease the number of turns of this second coil because the flux linking this full coil is number of turns into flux linking the second single coil, single turn. Okay, so by increasing N2 also, I can increase the flux linking in this second coil. So so that will get reflected in the mutual inductance M21. Okay, so reflect the formula for mutual inductance. It has got N1 and N2, right? Chapter number 7. Oh no, it's EMI chapter. What is this chapter? Okay, it's EMI chapter. No. That's fine. So mutual inductance M21, it depends on the turns of the coil. Okay, so if you increase the number of turns of the coil, the mutual inductance will increase. You know, increase the mutual inductance of the source coil, the flux produced by it will increase. Okay, so understood the concept? Because whatever flux is, see, in this particular case where it's shown in this book, here there's no concept of, because whatever is flux produced with this outer one, whatever can be produced, that can be get linked to this first coil, it's almost 100% because it's well inside this outer coil. Okay, but suppose I separate this coil and place it at a distance. In that case, if I decrease the distance between these two coils, then the mutual inductance will increase. Okay,